Hello, I'm Dave Brown. Today, we'll be learning about solid-state electronic devices, which are also called semiconductor devices. These devices consist of diodes, transistors, integrated circuits, and many other devices. But before we get involved with the devices, let's learn something about the basic electronic principles on which these different devices are based. Before you begin this series, you should have completed teletrain's programs entitled Basic Electricity 1 and Basic Electricity 2. From them, you will recall that all things surrounding us are made up of matter, and that matter is made up of atoms. The atom consists of a nucleus, which is made up of positively charged particles called protons, with electrons, which are negatively charged particles, revolving around the nucleus, much like the planets revolve around the sun in our solar system. This is a carbon atom. It has a nucleus made up of 6 positive charges and has 6 electrons, which are negatively charged, revolving around it. Each atom will always have the same number of electrons and protons. Carbon is one basic form of matter. It is called an element. Matter is composed of elements, and if the elements are different, the matter will be different. There are 102 different elements. The elements are made up of atoms, and the nucleus of protons and electrons in each atom determine the characteristics of the 102 different elements. The negatively charged electrons revolve around the positive charged protons in the nucleus in a particular arrangement called shells. The simplest element, or atom, is hydrogen, and it has 1 electron revolving around 1 proton. Helium has 2 electrons revolving around 2 protons. These 2 elements have 1 shell. All other elements have 2 or more shells with electrons distributed in the shells in a precise arrangement. If an atom has only 1 shell, that shell is considered filled when 2 electrons are in the shell. For atoms with 2 or more shells, the outer shell is considered filled when 8 electrons occupy the outer shell. Shells other than the outer shells may have more than 8 electrons. The number of electrons in the outer shell determines how the element or atom behaves. An atom with 8 electrons in its outer shell is called a stable atom. Atoms are always trying to become stable. They are always trying to completely fill their outer shell, and they do this by combining with other atoms and acquiring, giving up, or sharing electrons with other atoms. An example of this is sodium chloride, which is the chemical name for common table salt. Chlorine atoms have 7 electrons in their outer shell, and sodium atoms have 1 electron in their outer shell. The chlorine atoms and sodium atoms combine with the 1 electron in the outer shell of the sodium atom, providing the electron to go with the 7 electrons in the outer shell of the chlorine atom, so there will be 8 electrons in the outer shell, and the resulting compound will be stable. The attraction between atoms, which hold them together, is called bonds. The attraction between the chlorine atom and the sodium atom is called a bond. When 2 atoms are joined by 1 atom, acquiring an electron from another atom, the resulting bond is called an ionic bond. Another type of bond is called a metallic bond. In a metallic bond, there are a large number of the same type of atoms grouped together with a small number of electrons in their outer shells. These electrons are loosely attracted to the nucleus of the atom and can be considered to be more or less free electrons. The atoms do not acquire electrons from the other atoms, but are held together by an electron cloud consisting of the electrons in the outer shell moving about in a random manner. The positive charged protons in the nucleus of the atoms are attracted to the electron cloud and are thus held together by a metallic bond. The atoms in metals are held together by metallic bonds. The large number of free electrons causes metals to be conductors of electricity. You will recall from the films Basic Electricity 1 and Basic Electricity 2 that some materials were insulators and some were conductors. Materials which are held together by metallic bonds are conductors. Examples of conductors are copper, aluminum, silver, and other metals. There are a large number of free electrons in these materials. Materials that are held together by ionic bonds are insulators. Examples are glass, rubber, porcelain, plastic, paper, and other similar materials. There are no free electrons in insulators because in an ionic bond, the electrons of one atom are acquired by another atom and are tightly bound together. Remember, ionic bond, atoms acquire electrons. They're insulators. Metallic bond, electron cloud, conductor. We will now look at the third type of bond called a covalent bond. This bond is somewhere between the other two bonds. In the covalent bond, the electrons are shared between atoms. The electrons are not acquired, as in the case of the ionic bond, nor are they free, as in the case of the metallic bond. Some atoms have 4 electrons in the outer shell. The elements germanium and silicon are in this category. If several germanium atoms are grouped together, they will be held together by sharing electrons. The atom in the center will share 1 electron with the surrounding atoms, and the outer shell will now contain 8 atoms to make it stable. However, these electrons are not tightly bound together as in the ionic bond, nor are they free as in the metallic bond. Under certain conditions, these electrons can be moved in the germanium material, and here the material will conduct. Thus, the material is a partial conductor, or as it's called more often, a semiconductor. Covalent bonds are partial conductors or semiconductors because they are insulators sometimes, and under proper conditions, conductors sometimes. Remember, the 3 types of bonds are ionic, atoms acquire electrons, insulators. Covalent, atoms share electrons, semiconductors. Metallic, electron clouds, conductors. We said earlier that the materials held together by covalent bonds could sometimes be made to conduct. This can be done by adding some additional electrons to the material. The 2 most common materials used for semiconductors are germanium and silicon. Both of these materials have 4 electrons in the outer shell and are held together by sharing electrons with their neighbor atoms in a covalent bond. With 8 electrons in the outer shell, the atoms would be stable and thus would be an insulator. It would not conduct. However, the material can be made to conduct if a small amount of a certain kind of impurity is added. If we have a pure germanium crystal and add a small amount of phosphorus, the material will conduct. It conducts because phosphorus has 5 electrons in its outer shell. So the phosphorus atom will share 4 electrons with the germanium atom, and 1 electron will remain as a free electron. This free electron can move around through the semiconductor material and allow it to conduct. Other elements such as antimony or arsenic are also used as the added impurity to cause material to conduct. When elements with excess electrons are added, electron movement occurs. If an impurity element with 3 electrons in its outer shell is used, conduction will also occur. But the conduction is called hole movement, flow. If impurities such as boron, aluminum, or gallium, which have 3 electrons in the outer shell, are added to pure germanium, these 3 electrons will be shared with the 4 electrons in the outer shell of the germanium atom to form a covalent bond. but there will be one vacant space or hole. Conduction by hole flow can be proved by complex mathematics, but we can explain this conduction without the use of mathematics. There's a vacant space or hole in the covalent bond. An electron from another atom will jump into this space to complete the 8 electrons needed for a filled outer shell. But the electron that jumped into the vacant space left a vacant space or hole behind, which is filled by another electron jumping into that hole. This is repeated many times, and the holes appear to be moving through the material, hence hole flow. We often see transistors or diodes called germanium transistors or diodes, and silicon transistors or diodes. The material from which the transistor or diode is constructed is not pure germanium or silicon. We have seen that if it were pure, it would be an insulator. What is meant is that the device is made from mostly germanium or silicon with a carefully controlled amount of impurity added so that it will be a semiconductor. Some semiconductor materials contain an excess of electrons. In these materials, conduction takes place by electron movement. These materials are called N-type semiconductor materials. The N comes from negative charge of the electron. Other semiconductor materials have an abundance of holes. In this material, conduction takes place by hole movement or hole flow. These materials are called P-type semiconductor materials. The P comes from the positive polarity of the hole. In the N-type material, most of the conduction takes place by electron movement, and the electrons are the majority carriers. There will always be some uncontrolled impurities in the material, and in the N-type material, these uncontrolled or undesired inputs are holes, and these cause a small conduction in the opposite direction. The holes are called minority carriers. In P-type materials, the holes are the majority carriers, and electrons are minority carriers. When P-type material is joined to N-type material to form a P-N junction, we have the basis for both semiconductor diodes and transistors. The junction can be formed in several ways, such as grown crystals, diffused junctions, alloy junctions, and other ways. We're not too concerned with how the junction is formed, but rather how it functions and what it can be used for. When the P-type material with excess holes and N-type material with excess electrons are joined to form a P-N junction, some of the negatively charged electrons and positively charged holes will attract each other and thus neutralize to create a depletion region in the vicinity of the junction. After this initial movement of holes and electrons at the junction, there will be no additional movement and no conduction or current flow will occur. If an external voltage is applied across the P-N junction, the junction is said to be biased. If a DC voltage from a battery is applied with the positive terminal of the battery connected to the P-type material and the negative terminal connected to the N-type material, the P-N junction will conduct and a large current will flow. Under this condition, the junction is forward biased. If the negative terminal of the battery is connected to the P-type material and the positive terminal is connected to the N-type material, then only a very small current will flow. This small current is caused by the minority carriers and is called saturation current. For most practical applications, we can say that the junction does not conduct. Under this condition, the junction is reverse biased. An easy way to remember this is when positive goes to P and negative goes to N, things are matched up and current flows. But when negative goes to P and positive goes to N, things are all crossed up and no current flows. Remember, when the P-N junction is forward biased, there is high current flow. And when the P-N junction is there is little or no current flow. A semiconductor diode consists of one P-N junction. The word diode comes from the Greek word di, meaning two, and ode, the last three letters of electrode. Diodes will be covered in more detail in a later chapter. This is the end of Chapter 1. I'm Dave Brown for Teletrain.